Let's continue to discuss the formalism of quantum mechanics. In particular, I will go through some other important concepts that you usually see in quantum courses. And I will start from some considerations on states of the kind psi, written like this. So this is a ket vector. And then we apply an operator A to this state psi. I'm going to expand this state, in particular the state A psi, so I'm considering the action of A on the ket psi, and we can expand it in terms of the basis, and we can call the basis, for example, M. So we have several states, 1, 2, 3, ... an infinite amount of them in principle. And then when we take the inner product between two states, let's say N and M, we get the Kronecker delta NM because the states are orthonormal. And then we have some coefficients that we can call C sub M. And in order to differentiate actually the expansion of psi and the expansion of this overall state, I'm going to call this coefficient B sub M, because in principle they are different. If you remember in the previous video, when I considered the expansion of psi, we had something like this. So the index over which we are summing is just a dummy index, so we can call it N, or M, it's the same, but here the coefficients are different from these ones. C sub n, and then here we have n, whereas here we have the summation over m. So we can try to think that, these coefficients are different because here we have to expand this state, not this one. Now, at this point, we can use the completeness formula, for example. So I want to rewrite it in the following fashion. Summation over m, then we have the ket m and the bra m, and then we have A inner product with the psi. So here we have an inner product, you can see. So I have simply used the completeness formula because this is equal to the identity. So you get back that this is equal to this. It's quite simple to see that. And now with this kind of formalism, we can also rewrite the state psi by using its expansion. So let me go below. I will go here. So this equality is this one. And here we can sum over n and also over m. And then we have the ket m. Then we have the bra m. Then we have the operator A. Then we have n. And then we have C sub n. So I've used this formula. But we can also rewrite C sub n in a different fashion, so let me do it here. C sub n, if you recall from the previous lecture, but you can also see that from here and from this property, you can see that C sub n can be written as the inner product between the state n and the state psi. So we can rewrite the formula in this fashion. And now we can change our notation, because this one here is basically a matrix that depends on m and n, so we can rewrite it as A m n. This is our notation, where A m n is the mn element of a certain operator. So you can think of A as a matrix, and this is its element. When you take the inner product between the states m and n, like this. And this, of course, is C sub n. And if you rewrite the formula, so we can rewrite it like this, basically. We can rewrite it as summation over m, and then we have a summation over n. So I have rearranged the two summations. I have written the summation over m first. Then I have A m n C sub n, and then I have the vector, if you want, we can call it the ket vector M, or the state M, and if we compare this formula with this one, because they are equal, you can see that this expression is equal to B sub M. Simple as that. So basically we get the vector B equal to some matrix A applied, so I will put a tilde to denote the fact that this is a matrix, and then we apply the matrix to a vector C, because we can write that as Bm equal to summation over n am n c sub n. So we have the usual formula that we see in linear algebra, for example. So we managed to rewrite the same thing that we wrote in this notation with the operator acting on a ket. We simply rewrote it in the usual linear algebra formula, and that's something that should be understood from the fact that indeed bra and kets are simply vectors. So you have column vectors and row vectors, and basically you can understand quantum mechanics in this kind of conventional expressions where we have bra and kets, but they simply represent vectors. So we have the usual operations that we see in linear algebra. So that's why it's important. And let me also tell you that if A is Hermitian, as we said last time, we said that if A is Hermitian, its dagger is equal to A. And remember that the dagger represents a complex conjugation together with a transposition. So we take the transpose and then the complex conjugate. And of course, similarly, we can see this in the following manner. So if we take the element of the operator amn and we take the complex conjugate and the transpose, or vice versa. So if you take the transpose and the complex conjugate, you get the same thing. And this is equal to a n m star, if you want. And so this is equal to a n m dagger, but if it is Hermitian, this is equal to a n m, because if it is Hermitian, the complex conjugate transpose is equal to the matrix itself. So we have this identity, which is important for Hermitian operators. And let's do one more exercise to practice with the linear algebra formulation of quantum mechanics. In particular, let's remind ourselves of the Schrödinger equation written in the bracket notation. We have something like this. We have the derivative operator with respect to time acting on the state psi is equal to minus I over h bar, and then we have the Hamiltonian operator acting on the ket psi. Now we can rewrite the ket psi according to its usual expansion that we wrote earlier. So we can rewrite this as minus I over h bar. So this Hermitian operator is the Hamiltonian, and indeed it's Hermitian because its eigenvalues are non-complex, they are real. And then here we have the summation over n, c sub n, and then we have the ket n. And when we act with the Hamiltonian acts on the states n, and we can do the same expansion also here when we have the derivative, so we can use the expansion that I wrote in here for the ket psi. And then what we need to do is we need to take the inner product with m. So I'm going to take the inner product of this expression and also this expression with m. So it's quite intuitive what you have to do. You have to take m inner product with this, and then of course you have m here, and then you have m here, and remember that you need to expand psi. When you consider the expansion of psi like this, the derivative will act on this coefficient c sub n, because these states do not depend on time, only c sub n depends on time. And then you take the inner product with m, and remember the orthogonality, if you want the orthonormality of the states m and n. So when you take the inner product between m and n, you get the Kronecker delta and m. Remember this. You can write down the expression c sub m dot equal to minus I over h bar summation over n, and then you have the element h m n c sub n, like this. So this is another way to write down the Schrödinger equation, but if you want in the linear algebra notation, and if we take the complex conjugate of such expressions, you have something like this, I over h bar, so this minus becomes a plus, summation over n, h star, m n c sub n star, like this. Remember that the Hamiltonian is Hermitian, so we can also rewrite it like this. We write it as h without the star, but we have to change the order between m and n. So we have n m c sub n star, like this. Or actually, let's write c sub n star at the front here to denote the fact that here we have to sum over the first index. So I'm going to write it here. It's like considering a row vector multiplied by a matrix. Here we have the columns of the matrix, which have the same length of the vector here, the same length as the vector here. So this length is the same as this one, and if we have, let's say, n elements here, we have also n elements along the rows. So it's an n by n matrix, whereas this is a 1 by n vector. So this operation will give rise to a 1 by n vector, which is the same as this one. So this is 1 by n, if you want. And we can also use another notation, another type of notation. In particular, this can also be written as the derivative acting on the bra psi. So in this case, it's a bra, because remember that when we write a bra, we think of a row vector, and there is also complex conjugation in the bra. And here we have I over h bar, and then we have the state, the bra psi, which is the same as this one, but in this case we have the derivative because there is this dot, and then we have the Hamiltonian. So another kind of notation is this one. Basically, it's like taking the usual Schrödinger equation in the bracket notation, so it's this equal to this, and then you take the complex conjugate transpose, and you are led to this expression here. And in the next video, we will recap unitary transformations, which are also important in quantum mechanics. So I will conclude this video here, and we will continue in the next one.